All right, in this video we are going to talk about weighted graphs and Kruskal's algorithm. So a weighted graph is a graph together with a weight function. The weight function is a function from the edge set of the graph into the real numbers. And in this we are talking about just regular graphs, simple graphs. Here you can see an example of a weighted graph. I have just a regular graph, and then on the edges I have these numbers attached to the edges, and those numbers are the weights of the graph. And so the weight of a subgraph of H, of a weighted graph, is the sum of the weights of the edges in H. So whatever the subgraph is, you would just add up all the numbers, add up all the weights of the edges that are in the subgraph H, and that's the weight. All right, so that's a weighted graph. And what we want to do, sort of a fundamental problem of this in this area, is to find a spanning tree of the graph, of a weighted graph, that has the smallest weight. The graph has to be connected, right? And so one of the algorithms that you can use for this is called Kruskal's algorithm. And so given a connected graph G, right, this algorithm is going to produce a spanning tree T of G with the smallest possible weight. All right, and so the algorithm goes like this. First off, select an edge of smallest weight and add it to T. All right, so whatever the smallest weight is, edge, you're going to add that. And if there's multiple edges with the smallest weight, then it doesn't really matter which one you pick. So if there's a tie, you can just choose arbitrarily. All right, so you would add that into the tree T. And again, what we're doing is kind of growing a tree as we go along. One big difference between this algorithm and the one that we looked at previously is that there will be times in which this graph that we're growing, it will result in a tree, but it won't be a tree at every stage. Sometimes it won't be connected. Okay, so it is a forest at every stage. It will not contain any cycle. All right, so we add the edge of smallest weight into the T, and then what we'll do is we'll select an edge with the smallest weight that is not in the existing forest and add it to T. All right, and that's provided that the addition of that edge does not create a cycle. All right, and so basically we are going to go through and check to see, right, every edge, and you're pretty much doing it in order of the weights, right? So from the smallest weight up to the largest weight, you're going to go through and you're going to look at that edge, right, and then you're going to add it into the graph of add it into T, the subgraph T, if it does not create a cycle. All right. Now step 3 says check to see if T is a spanning tree. If so, stop. If not, repeat step 2. All right, so once you have a spanning tree, there's no point in going on any further, right? If you have a spanning tree and then you add any edge to that, it's going to introduce a cycle. So at some point, right, once you have a spanning tree, there's no point in going on and repeating that. So that's just kind of an optimization there that you really don't have to check every edge. You just have to check until you get to a spanning tree. Okay. So this is an example of what's called a greedy algorithm. You just try and take the smallest you can and hope that it works out. And in this case, it does work out. And we will prove part of the fact that it works out. And the other part, we will not prove that in this video. It's a little technical. So the greedy algorithm in this case turns out to be one that works, right? This is going to give us a minimal weight spanning tree. The thing is, it doesn't always work, right? The greedy algorithm. Sometimes there's just situations where that doesn't apply, or where it doesn't give you the optimal thing that you want. All right, let's take a look at this example. All right, and so here is our weighted graph. it is connected, right? And so we are going to start with Kruskal's algorithm. So looking at the edge of minimum weight, it's right here in 3. So that's what we would do. We would start, and I'm just going to color the edges red as we go through, all right? All right, and then the next lowest weight edge is 4, right? And so we have 2 that are weight 4, so it really doesn't matter which one you add in there. I just happen to pick this one right here. Okay. All right, and then the next lowest weight is this one right here. And so that one gets added in. And you can see that this graph is not connected, right, at all. All right, and then the edge with the lowest weight here is this one with 5, so that would be added in. It doesn't make a cycle. Then the edge with the next lowest, or the lowest weight, is this one 6 right here. The thing is if we add that edge in, right, we are going to introduce a cycle, right? This cycle right here. So that one, we can't add that one in. All right, and so then the next lowest one would be this one right here. Okay, this one with 9, and so you can see right now we have a spanning tree. All right, it's spanning subgraph. It's connected. It contains no cycle, right? So it's a spanning tree, and this is the minimal weight spanning tree, right? If you add up all of the weights, that would be the spanning subtree, or a spanning subtree with the smallest possible weight. All right, and so that's it. So it works pretty well. So some things about this, right, kind of don't seem obvious. Number one is that if you did this algorithm, you know, how is it correct all the time, 100%? You might buy the fact that it gives you the minimal weight, although the proof of that part is actually, to me, more difficult than the proof that this thing is a spanning tree. So the thing that seems like maybe it might be obvious, that this is going to give you the smallest weight spanning tree, to me is the more difficult part to prove. So we're not going to do that in this video. The thing that is not totally obvious is that this is always going to work out to be a spanning tree no matter what. So, and you can see, right, in this case we have some steps in this process where the graph is not connected. So how does this always turn out to be connected? All right, so let's go through and prove that. So the first part is that the tree that we result in, right, when we stop, is contains no cycle. Okay. And that part is pretty obvious, because if there's going to be a cycle, we just don't add the edge in, right? So no cycles are created at all. We're very explicit about that when we go through. If an edge is going to create a cycle, well, we just skip it and move on to the next one. Okay, so there's no cycles. That's pretty straightforward. So next is that T is a spanning subgraph of G. So therefore it has to contain, right, all of the vertices of G. So here I want to draw a picture, so let me see if I can just draw a small picture here as we go through this. Okay, so here we're going to prove that T is a spanning subgraph of G, right? The graph that we get as a result of this Kruskal's algorithm. So suppose it's not a subgraph of G, right? So what that will do is that will give us some vertex V. That's in G, but not incident with any edge of T. Okay. So in other words, we know that G is connected, right? And so therefore you can't have an isolated vertex V. So this vertex V that's not in T, right? It has to have some edges, at least one edge coming out of it. All right. So we know that there's edges coming out of this vertex V. All right, and so what I'm going to do is just pick any edge that's incident with V, right? So, and call it E. So it doesn't really matter which one you pick. I'm just going to call this one E, okay? All right, and so when we went through and did the algorithm, right, with this, we know that this edge E was not picked, right? Because we know that no edge that's incident with T or incident with V is in T. So this edge was not picked to be part of our tree T, right? And so what that means is the only reason why we are not picking an edge, why we don't pick an edge, is because it introduces a cycle when we add it in there, right? So what that means is if we take the graph that we get from this process and we add the edge E to it, it contains a cycle. So what that means is that when I add E in there, right, then all of a sudden T, which is the red graph that we had in the picture, all of a sudden now it contains a cycle like this. I don't know exactly what it looks like, but it looks like so, okay? All right. And so what that means is that that vertex V had to be incident with some other edge of T, right? This red graph. That's the only way that it could have been in this, that adding this edge E in there will give you a cycle. So that means it had to be some other vertex there, and that's a contradiction, right? Because of the fact that there had to be some, if V, right, is not in the graph T, that means that, you know, no vertex, a V is not incident with any edge that's in T, but it had to be, right, because of this argument right here, right? When we add E in, it had to be part of a cycle. A cycle in this graph that we're looking at has at least 3 edges, so one of these other edges, right, had to be involved in that cycle, and therefore had to be in T, okay? So that's a contradiction. So that makes T a spanning subgraph, right, of G. So now we know that the graph T contains all of the vertices of G. So the last thing we're going to prove here is that T is connected, okay? And so again, we are going to suppose that it is not connected, all right? And again, I'm going to draw a picture here. Okay, so if T is not connected, that means we have, what we end up having is that T will have multiple components, right? It'll have 2 or more components. So what you end up with, you say you might have a component here. Right, whatever that looks like, and some other component. I'm not drawing the full graph, right? Just trying to illustrate this argument here. So here's one component and here's another component. All right, and so there's got to be vertices that are in different components. And remember, components, right, are maximal connected subgraphs, right, of the graph G. And so what that would mean is that there is no path in T between V1 and V2, right, if they're in different components, right? So kind of like my picture has here. There's no path using only the, and T is going to, these red vertices and edges are going to indicate, you know, vertices and edges that are in T. So there's no way to get from V1 to V2 or vice versa, okay? So what you end up with is these 2 vertices V1, V2 that are in different components of T, but that are incident to a common edge that's in G, right? Remember, G is connected. So that means there is a path between any 2 vertices, right? Okay. And so what you end up with is this situation right here, right? That I have 2 components. V1 is in one component, vertex E2, V2 is in another component, and that there is an edge that's in G that goes between those 2 that's not in T, okay? All right, and that's the edge that we're calling E. Now you may say, well, how do I know that there's an edge between any um, any vertex in the one component and to one in another component? Now that's because the graph G is connected, right? And so therefore, in G, right, there is between any two vertices, right, a path that goes from one to the other. And we know that we're assuming T is not connected, right? And so T can't be all of G. That means there has to be some edge, right, that is some edges, right, that are not in some edges that are not in G there's some edges. Sorry, there are some edges of G that are not in T, right? And so those edges, right, their endpoints, right, have to go between two vertices that are in T. So there's got to be some setup like this, okay? All right. And so, again, T plus E contains a cycle. So what that means is that there is a cycle, right, going from, that includes, just by adding this edge right in here, it goes in T. So there has to be some other edges, right, going around here or someplace like that that make a cycle like so. Okay, why is that so? Well, remember, that's the only reason, right? What we do essentially in Kruskal's algorithm is to look at every edge and in the order from smallest weight to highest weight, and we only add that into the graph if it does not make a cycle. So the fact that E is not in this graph means that it makes a cycle in T. So just by that one little addition, right, in here, we get a cycle, and that cycle had to have include the endpoints V1 and V2, right? And so what that means is that now there is a path between V1 and V2, even though they're in different components, right? Because they're in a cycle, I can find two paths, and so I can find the one that doesn't use E right here. All right, and so that means that there is a path in T connecting V1 and V2 together, and that's a contradiction. Okay, so that means that this situation can't really happen. T has to be connected. Okay. The last part about the fact that this gives you the minimum weight, we're not going to prove in this video. There are a couple of, if you look in this section in our textbook, right, there are two exercises. I think they're the very last two in this section, and they outline a proof of a special case that this does give you the minimum weight spanning tree. All right, but that's definitely a little bit more complicated than what we've done here. So I'm not going to put that into this video. All right, and so that is it for this one.